Okay, if we look at this problem, everyone got the same correct answer, looked like, that the hydrogen iodide concentration is equal to 2x from our chart, so it's 0.312 molar, and the hydrogen and iodine are both 0.2 minus x, which is 0.044 molar. So everybody got the same correct answer. So looking at how you got there, we set this up. We had 0.2 moles in a 1 liter flask, so each of the initial concentrations was 0.2 molar. We had 0 hydrogen iodide. This problem was different because of the 1 to 1 to 2 stoichiometry. So I set this up as minus x, and plus 2x. Now I did see one group that had 0.5x, 0.5x, and x, and there's no problem with doing it that way. For me, it's easier to use x, x, and 2x because when you get to some weird problems where you have 4, 3, 7 as the coefficients, you don't want 1/4 of an x and 3/7 of x and things like that. So it's just easier to go with whole numbers in my opinion. So then at equilibrium, we get 0.2 minus x and 2x. We know the K value, so we plug in the hydrogen iodide concentration, square it, divide by the hydrogen times the iodine, and as we follow through the math, taking the square root, x is 0.156, and then that leads us to our answers. So it looked like everybody went through this one a lot more easily, which is good to see. Now let's talk about the math. We talked about the quadratic equation, and the quadratic equation is not that big of a deal, but it's a nuisance. And especially when you're not allowed to use your fancy calculators. And you have to remember where I came from, that learning all of this in a time when there were no calculators and you had to solve the quadratic by long division, it was a lot more of a nuisance than it is when you have a calculator. I can assure you of that. So we think about this. If we have a situation where the K value is small, we said that when the K value is small, we don't have very much product. So that means not very much reactant gets used up. So when K is small, and we define small as less than or equal to about 1 times 10 to the negative fifth, then the amount of material that actually reacts is so small that with sig figs, when you subtract that concentration X from the starting concentration, you essentially get the starting concentration. So we can ignore X and we can assume that the starting concentration and the equilibrium concentration are the same. But if you're multiplying that X out, you can't ignore it. So let's look at an example where we go through this and make this kind of assumption. What's the hydrogen concentration at equilibrium for this water-gas equilibrium? If the initial water concentration is 0.1 molar and Kc is 7.3 times 10 to the negative 18th. Is that a small K? Yeah, that's really small. So it's safe to make these assumptions. So we'll start off, like always, write our equilibrium law. K sub C is equal to the hydrogen concentration squared times the oxygen concentration. Divided by water because it's water gas. And because of the 2, we square the water concentration. So now we'll set up our concentration table. We have an initial concentration of 0.1 molar. That's all the information we're given. So as we fill this in, we say, well, to start, I have no products, so I have 0 and 0. Since there's a 2 here, minus 2x, 2x, and x. At equilibrium, 0.1 minus 2x, 2x, and x. Now, let's look at the equation. If we plug in K sub C, 7.3 times 10 to the negative 18th is equal to 2x, the quantity squared, times x, divided by 0.1 minus 2x, the quantity squared. Now, what kind of mess is that going to give me mathematically? It's not a quadratic. What is it? What kind of mess are you going to end up with here? What do you get right on the top? Cubed. You get an x cubed equation term, then you're going to get x squared and x. So you're going to have not a quadratic, but a cubic equation, which you don't have a clue how to solve without your graphing calculators, because you never learned to solve those by hand graphing, have you? They don't do that anymore. Yeah, they don't do that anymore. I know. That's how I learned to solve them. So we really don't want to solve this mess. At least I don't. So what we do is simplify if possible. Because k is so small, it's possible. So when we think about this, because this is so small, 2x is very small and insignificant compared to 0.1. So we can say that 0.1 minus 2x is about equal to 0.1. Now, anytime you make these assumptions, you always have to go back and check and make sure it was really okay to do. But we're going to go ahead now and try and see if it is. So now, 7.3 times 10 to the negative 18th is equal to 2x, the quantity squared, times x, divided by 0.1, the quantity squared. So now I rearrange. 7.3 times 10 to the negative 18th times 0.1 molar squared is equal to 4x cubed, because 2x, the quantity squared, is 4x squared times x is 4x cubed. So 7.3 times 10 to the negative 20th is equal to 4x cubed. 7.3 times 10 to the negative 20th divided by 4 is equal to x cubed is equal to 1.8 times 10 to the negative 20th. So x is equal to the cubed root of 1.8 times 10 to the negative 20th. So now x is equal to 2.6 times 10 to the negative 7th molar. So, what's the hydrogen concentration at equilibrium? Well, the hydrogen concentration is equal to 2x, so that's equal to 5.2 times 10 to the negative 7th molar. So make sure you go back and answer the question. Now let's go back and check, was our assumption okay? My starting concentration was 0.100 molar. If I subtract from that 2x, 5.2 times 10 to the negative 7th, is that going to be insignificant when I subtract? Absolutely. So it was a good assumption, and it saved us a lot of aggravation mathematically. Okay, now you go ahead and try the one on the next page. See if you can make the assumption that x is small and solve.